In this chapter, you're going to learn about what are called random variables. So let's start off by thinking about what a non-random variable is. So non-random variables are the variables that you're used to so far. And these are values that we can work out, and we definitely know what they're going to be. So for example, we could say that S is the distance traveled by a car in 2 seconds when it's moving at a speed of 4 meters per second. And this variable S is called non-random because we can calculate its value. We can use distance equals speed times time to know that the value of S is 8 meters. So let's look at an example of a random variable. We call random variables, we denote them by a capital letter. So in statistics, if you see a capital letter as a variable, it means that it's random. And by random, we mean we don't know what its value is before an experiment or before an event happens. So for example, we could say that capital X is the number shown on a dice after we roll it. Now, X is random because before we roll the dice, before the experiment happens, we don't know what the outcome of X is going to be, capital X. Well, what we can write down though, is we can write down what are the possible values that capital X could take. So we know that when we roll the dice, X could either be 1, 2, 3, 4, 5, or 6. These numbers here, the possible outcomes of our random variable, are called the sample space of the random variable. Another term that you'll see if you research this topic outside the A-level, which is more used outside the A-level, is the support of X. But we're going to use the word sample space. Now, what we could do is we could write down underneath each of these values of capital X, these possible values, what's the probability that capital X is equal to each of these values? So here I could write a sixth because that's the probability that X is equal to 1, probability that X equals 2, etc. So here we're assuming that it's a fair dice. So all the probabilities are equal. Well, each of these values of the sample space here, we denote by a little x. So when you see little x, that's not random. Little x is the specific values that capital X could take. And underneath here, this is the probability that capital X is equal to 1. What's the chance that our random variable after the experiment is equal to 1? Well, that's a sixth. Here, similarly, this is the probability that capital X is equal to 4, for example. And so here in this row, we've got the probability that capital X, our random variable, is equal to one of the specific values of X above. So we write this as the probability that X is equal to each specific value of X. And as we move along the table, this value of little x changes. So this is how we write this. Now this whole table here is called a probability distribution. And it's called a probability distribution because we know that all the probabilities have to add up to 1. Because one of these events must happen, and we know the sum of all possible outcomes is 1 when we add up the probabilities. And it's called a distribution because it tells us how is that one probability of 1 distributed between the outcomes of the random variable x. Let's look at one more random variable, perhaps a slightly different one. Let's say we're playing a lottery and the probability of winning the lottery is 1 in 100. And let's say the probability of losing the lottery is therefore 99 100ths. Okay, we might want to define a random variable, which is y is the winnings or the amount won, amount of money won from the lottery. Let's say that the winnings are, so if you win £10,000. Okay, so let's write down what the probability distribution then is of y. So we're going to have some specific values that y could take, and we denote that by little y. So y is the amount of money won from the lottery. So we could either win £0 if we don't have a winning ticket, or we can win £10,000 if we have a winning ticket. So these are the possible amounts of money that I could win from the lottery. So underneath we're going to write the probability that capital Y is equal to each of these specific values of y. So underneath here I need to write down what's the probability that I win £0 in the lottery. Well, that's 99 hundredths, because that's my probability of losing. What's the probability that I win £10,000, or the probability that capital Y is equal to 10,000? Well, that's the probability that I win, which is 100th. So this is the probability distribution for the random variable y, the amount of money won in the lottery. Okay, let's look at example 1 then. So 3 fair coins are tossed, and we want to write down all the possible outcomes when the 3 coins are tossed. So you might be able to just write down what the outcomes are, but if you wanted to do this formally, you could do it quite easily with the tree diagram. So the first coin is either going to be heads or tails. So this is the first coin. If I get heads on the first coin, then the second coin could either be heads or tails. If I get tails on the first coin, then the second coin could still either be heads or tails. And then finally, on the third coin, if I get heads and then heads, I could get heads or tails on the third coin, etc. And because these all the coins are fair, we know that the probability is always going to be a half and a half for each of these events. So at the end here, we can write down what are the, let's call it the outcome of the experiment. So here I'm going to get heads, heads, heads. Here I'm going to have heads, heads, and then tails. And we could complete the list. So these are all the possible outcomes, and we've got 8 possible outcomes. And that makes sense because we've got 3 events happening, and each event has 2 possible outcomes. So it's 2 times 2 times 2, which is 8 outcomes. Well, we've got this random variable x, which is defined to be the number of heads when the 3 coins are tossed. Before we do that, we should probably write down what's the probability of each of these outcomes. And actually, all of these outcomes have the same probability. And that's because when we times along the branches to get to the outcome, we're always going to do a half times a half times a half, half times a half times a half. So all outcomes have the same probability, which is a half times a half times a half, or 1/8. So all of the outcomes are equally likely because there's 8 outcomes. So let's have a look at this random variable x then. So x is the number of heads when the 3 coins are tossed. So on the side here, I'm just going to write down what x would be equal to. So let's write that here. I'm going to use the little value of x because these are the specific values that x could be equal to. So if this is the outcome, then we've got 3 heads. If this is the outcome, then we've got 2 heads. If this is the outcome, then we'd have 2 heads. If this is the outcome, then we'd have 1 head. If this is the outcome, we'd have 2 heads. If this is the outcome, we'd have 1 head. If this is the outcome, we'd have 1 head. And if this is the outcome, we'd have 0 heads. So these are the possible outcomes for our random variable x. These are the values that our random variable x could take. So let's write down a probability distribution for x then. And we're going to do it in a table first. So we're not going to write down 0, 1, 1, 2, 1, 2, 2, 1, 3, because that doesn't make any sense to include the same value of x. All we want here is what are the possibilities that x could be? Well, the possibilities are 0, 1, 2, or 3. And then underneath, we need to write down what's the probability that our random variable x, capital X, the number of heads, is equal to each of these specific values of little x. Well, to work out what's the probability of having 0 heads, capital X being 0, well, there's only one outcome which has 0 heads. And we know that the probability of that outcome is 1/8. If we wanted the probability of there being 1 head, so capital X equals 1, we've got this outcome, or this outcome, or this outcome could happen. So you should know from the previous chapter that we've got 1/8 plus 1/8 plus 1/8. So this 3/8 is the probability of having that outcome, or that outcome. This one, or this one. The probability of getting 2 heads is either this outcome, or this outcome, that one, or that one. And that has 3/8 probability as again, because it's 1/8, add 1/8, add 1/8. And the probability of getting 3 heads is only one outcome, which has probability 1/8. And at the end, you should check. In part 2, we're asked to write this probability distribution using a probability mass function. So let's have a look at what a probability mass function is. So the way that we write a probability mass function, or just a function, is the probability of x equaling a specific value of x. Well, this value is going to change depending on what we put as that little value of x. For example, if I put in the probability of x equaling 1, so when little x equals 1, then this probability would be 3/8, this value here. So what we're going to do is we're going to write this using a big bracket like this, and we're going to say, well, this probability is going to be equal to 1/8 if I put little x equal to 0. It's going to be equal to 3/8 if I put little x equal to 1, etc. 3/8 when little x equals 2, and it's going to be 1/8 when little x equals 3. So from this, I could read off each of the probabilities. Say I wanted the probability of having 3 heads. So I'd say, well, that's the probability of x equaling 3. So I've put little x equals 3, and I look at my function. When little x equals 3 heads, I get the probability is 1/8. Well, we could write this in a more compact way, actually. We could combine x equals 0 and x equals 3 into a single statement. Because if I put x equals 0 or I put x equals 3, I get 1/8. So we could actually say that this is equal to 1/8 when x equals 0 or 3. And I could say that the probability is going to be 3/8 when little x equals 1 or 2.